Up till now, we've covered the basic building blocks of ROS2: nodes, topics, services, parameters, and launch files. On the surface, they don't seem to have a lot to do with robotics. That's because ROS2, at its core, is a communication framework, and it can take some time to learn that framework before jumping into more advanced topics that actually pertain to robotics. Well, we've finally reached that point. In the next 2 episodes, we're going to talk about TF2, which is the ROS2 library for transforming between coordinate frames. We'll demonstrate it only in Python, as there's a good bit of conceptual knowledge to wrap your head around. I'll provide a demo in C++ in the course GitHub repo should you need it as a reference, but we'll stick with the higher level Python so we can focus on the concepts. Let's get started. As I mentioned, we've talked about the underlying communication parts of the ROS2 framework for the past 9 episodes. Now we're going to introduce TF2 as well as the Turtlesim environment so you can see how all of this plays together to make robots work. Robots need to operate in the real world and interact with their environment. In most cases, we need to have a sense of space about the robot, which usually means a set of coordinates with x, y, and z axes, assuming we are working with Cartesian coordinates. In most simple cases, we care about the robot's absolute position in our map or world coordinate system. This coordinate system is also known as a frame in TF2 terminology. When we talk about absolute position, we mean in relation to a frame that we assume is fixed, such as the environment the robot is operating in. We might also have a heading of the robot, which way it's pointing and possibly its speed and acceleration in that direction. We'll just focus on the position and heading for now. In basic 2D or 3D systems where we have knowledge of the map around the robot, think of something like a video game character moving through a pre-built world, it's easy enough to know where the robot is in that frame all the time. Let's say we want the robot to line up with a target and move toward it. In something like a video game or simulator where we control the whole environment, this would require some fairly straightforward trigonometry. But it starts to get a little trickier when you have things like sensors or manipulators that are offset from the center of the robot. For example, the sensor or manipulator arm might move independently of the robot's body, like on a rotating joint. Now it starts to make sense to talk about things from the robot's frame of reference. We can move or figure out the location of something in the robot's frame of reference pretty easily. Where is that sensor or manipulator in x, y, and z coordinates relative to the robot body? From there, we can use the TF2 library to help us translate or transform coordinates, headings, and so on in one frame of reference to another. Recall that a frame is a coordinate system. A transform describes the special relationship between 2 frames at a given moment in time. That allows us to get the location of the sensor in the world frame coordinates or let us easily navigate the robot body toward the target despite the sensor offset. This is a relatively simple example and one that could be solved with a bit more trigonometry, but TF2 is easily scaled up to far more complex problems. Let's take a manipulator arm for example. These arms often have 2 or more servos to move the tool head around in space. Now, let's say you want to move the tool toward a target, and we'll assume the tool is a gripper. You might have a set of cameras or sensors to know where the target object is in relation to the base, which we will assume does not move. But then you need to figure out how much to move each joint by to get the gripper to the target. As you can imagine, the math for this gets very tricky very quickly. This is where the TF2 library can save us a lot of headaches. It will handle much of this transformation for us, so we can worry about making servo adjustments relative to each frame rather than calculating them based on the absolute or base frame. Now, let's say you have a robot operating somewhere in the real world. We'll assume this is a self-driving car that needs to navigate roads, avoid cars and pedestrians, and watch out for other obstacles. Here, we don't really have a world frame. Maybe GPS can get us close, but not to the level of precision we need to navigate successfully. Not to mention, map data might be out of date and wouldn't include all of the obstacles you might find on a road in real time. This is where the study of simultaneous localization and mapping, or SLAM, comes into play. SLAM is where the robot tries to construct or update a map of its surroundings while also keeping track of its location within the map. As you can imagine, this is a tricky problem that includes a lot of current research efforts. We can use a variety of sensors like cameras, LiDAR, or radar to continuously generate snapshots of the robot's surroundings. SLAM then attempts to update the world frame map and determine where the robot is within that map. If you're trying to do anything with SLAM in ROS2, you will most likely be working with the TF2 library. Transforming coordinates between frames of reference is crucial in SLAM. TF2 allows every part of the robot to talk in a common spatial language and keep all of the coordinate systems in sync over time. This works through a combination of broadcasters and listeners. Let's assume we have two mobile robots that operate in a simple two-dimensional environment. We'll call them Turtle1 and Turtle2. The environment has its own set of coordinates, known as the world frame, and we'll assume these don't change. Turtle 1 and 2 can move freely within the coordinates of this 2D world, and each has its own relative frame of reference. Turtle 1 has a front-facing camera that's offset from its body, so we can give this camera its own frame of reference too. Maybe we want the two turtles to move in such a way that Turtle 2 tries to stay in front of the camera. Who knows why? This is just a very basic example. To make this work, we need TF2 to track all these frames and how they move relative to each other. This is where broadcasters come in. A broadcaster is some code, usually part of a node, that publishes the transform between the child frame and the parent frame. You can think of a broadcaster as a specialized publisher that says, here is where the child is located relative to the parent right now. So the Turtle1 broadcaster would broadcast the transform from the world frame to the Turtle1 frame. As the camera frame is a child of Turtle1, the camera node would broadcast the transform from Turtle1 to the camera. Turtle2 would broadcast the transform from the world frame to Turtle2. Each transform is published periodically, often on the order of about 10 times per second, so that other nodes can keep up to date on how all the pieces are moving relative to each other. To make use of these transforms, we need a listener. This is similar to a subscriber. It listens to the transforms being broadcast to a specific topic and stores them in a buffer. This buffer allows the listener to get the transform between any two frames, not just parent and child, at any given time. As transforms are time-stamped, TF2 will also interpolate between snapshots if needed. So now a node controlling Turtle2 could implement a listener that periodically asks the TF2 buffer to figure out where the camera is relative to Turtle2's frame. Using that information, Turtle2 can calculate how far off it is from being in front of the camera and make the necessary movements to get there. The beauty of TF2 is that Turtle2 does not need to understand all the intermediate transforms and how everything relates to the world frame. It just asks for the current transform between itself and the camera, and TF2 handles all the math behind the scenes. While it requires a bit of setup in your nodes, it can save you a lot of math and headaches, especially as you add more moving parts to your robot. We're going to start with a very basic example. I'll first introduce you to Turtlesim, a 2D robot simulation environment based on Logo from the 1960s. It gives us a movable character that we can control through various commands. We'll make a simple broadcaster that translates from the world frame to the turtle's frame of reference. Then we'll examine the transform using a built-in command line tool. In the next episode, we'll expand this example to include more broadcasters and a listener that actually does something with the information. If you head to the documentation page for your particular distribution of ROS, you can go into concepts, intermediate concepts, and find some information about TF2. Feel free to read through this as it gives you an overview of what TF2 is, similar to the stuff we just talked about. If you go to tutorials and then intermediate TF2, you get information about how to use TF2, and we're going to demonstrate most of this and build up a broadcaster and listener so you can get a sense of how TF2 works over the next couple of episodes. Let's go to our container. We're going to go to this second desktop and bring up a terminal. I want to talk about Turtlesim first so you can get familiar with it because we're going to be using that to demonstrate TF2. If you enter ROS2 run Turtlesim node, you will get the Turtlesim environment. This is a very basic simulated robot environment and it's only 2D. We've got our sprite in the middle, which is some random turtle. And we can move this turtle around this 2D environment and it will trace a line behind it. If you've ever used Logo, it is very similar to that. So I'm going to let this run in this tab. And I'm going to open up a new tab and we're going to use the teleoperated key functionality. So I'll type ROS2 run Turtlesim turtle teleop key. Now I can use the arrow keys as long as I have that tab selected, and I can move the turtle around. So left and right rotates it left and right, and forward and backwards moves the turtle in those directions. You can also use the GBV, C, D, E, R, T keys to rotate to absolute orientations. So if I push B, you can see the turtle turning there, and you can push F to make it stop. If you go to the first tab, you can see the instructions being received by Turtlesim. Let's go back to our teleop key tab. Let's open up another terminal, and we will put it in the corner over here. Let's do ROS2 topic list. You can see the topics available for the Turtlesim. Notice that we can spawn multiple turtles in the Turtlesim environment. The first one is named Turtle1 by default. You can spawn them and rename them if you want, but by default they will be named sequentially. So the second one would be Turtle2, Turtle3, and so forth. And you have the topics within that namespace. So in the Turtle1 namespace, we have these topics, and the one we care about is pose. Keep in mind that pose is a combination of position and orientation in space. If we echo pose, you can get a sense of the turtle's position in space. Notice that it's given by XY coordinates. That's in the world frame here. We have theta, which is its heading in radians. And then we have linear velocity and angular velocity, how fast it's moving forward and backwards, and how fast it's turning. So that information gives the entire pose for this turtle in this 2D space. So if I go back to the teleop key terminal and I move it around, so if I go forward and backwards, you can see X and Y changing, and you can see how the linear velocity updates as well. If I move left and right, you can see how the turtle turns in space and theta updates, and you see the angular velocity changing as well. So a combination of those, and you can move the turtle around and get a sense of where the turtle is, its heading, and its velocity in space, thanks to this pose information. Let's press Control-C. Let's do ROS2 topic list again. Let's take a look at that Turtle1 command velocity topic. You can see it has a message type of geometry messages message twist, and there's one publisher and one subscriber. That publisher should be the teleop key over here, and the subscriber should be the turtle itself. Let's use interface show to take a look at that interface, and you can see it's composed of two vectors, each given by X, Y, and Z. The first is linear, and the second is angular. So this twist interface works in 3D space, but we're only using a couple of pieces of it for this turtle. Specifically, linear X describes the forward and backward velocity of the turtle, and then angular Z describes the rotational velocity of the turtle around its Z-axis. If we assume Z-axis is coming out of the screen here, then the twist is the best way I like to think about it. The angular velocity around that axis is how much the turtle is turning in its 2D space here. To control the turtle programmatically, you need to create a publisher and publish to this command velocity topic. So let's try that manually here. We'll call ROS2 topic pub. We'll say once, so that only does this once rather than continuously using this pub command. We'll give it the topic name, turtle1 command velocity. We will give it the message type or the interface, geometry messages, message twist, and then we will fill out that message. So in that we will say linear, that's a combination of X, Y, Z. X is going to be 0.5, the others are 0. And then the angular, where the X and Y are 0 and Z is 1. This should cause it to move in a circle. So if we run that, sure enough, you see the turtle move a little bit in a circle and then stop because of that once flag. I'm going to push up to get that command again. I'm going to go back And I'm going to get rid of this once tag. And we're going to do rate 1. So that should publish it once per second. And when we run that, you can see the messages being published once per second. And you can see the turtle making a nice little circle here. So that should give you an idea of how to programmatically control the turtle by publishing 2 topics. Keep that in mind for the challenge that I will issue at the end of the next episode. Let's Control-C to stop that. Let's go over to our first desktop. I'm going to open up VS Code, and now we're going to start working on a demo TF2 application. Yes, I trust the authors. Let's make that bigger. As I mentioned, I am going to only do this in Python, but I will have a C++ demo available if you'd like to look at the code. The reason is I want to focus on just the concepts, and Python I find is a little easier to read. So let's go into source, mypy package, and in here, we're going to create a new file called util.py. This is where we can put some helper functions that can be used throughout our nodes. You zoom in a little bit so you can see what's going on. Something to note about Turtlesim, as we saw when we looked at its pose, it gives rotation in Euler angles, which is the very common roll, pitch, yaw. It's just 3 values. Well, in reality, it just gives us yaw. It's the rotational velocity around the z-axis. Quaternions give us the same information, but with 4 values instead. There's 3 for each of the x, y, z components. This creates a unit vector, and then 1 for the amount of rotation, w, so the weight or magnitude. I won't dive into the specifics here behind the math of quaternions, just know that we have to use it when dealing with TF2. ROS1 had a conversion built in, and you can use that package still, but for whatever reason, ROS2 did not include that package. So we need to do this conversion ourselves, and it's fairly straightforward. We first need to break the yaw, pitch, and roll parts into their cosine and sine components. So for each value of roll, pitch, and yaw, we will multiply it by 0.5 and then take the sine and cosine of that and store it in each of these variables. To get the w value of the quaternion, we multiply the roll, pitch, and yaw cosine components, add that to the roll, pitch, and yaw sine components. To get the x component for that unit vector, we need to multiply the sine part of the roll value with the cosine parts of the pitch and yaw, and then subtract the cosine of the roll times the sine of the pitch and yaw parts. I'm going to go ahead and fix this spacing so it all lines up. To get that y component, we'll multiply the cosine of that roll part by the sine of the pitch, and then by the cosine of the yaw. And then we'll add that to the sine of the roll times the cosine of the pitch times the sine of the yaw. Finally, for the z component, we will multiply cosine of the raw times cosine of the pitch times sine of the yaw. And then we will subtract the sine of the roll times the sine of the pitch times the cosine of the yaw. And then all we need to do is return those qx, qy, qz, and qw components. I'm going to add a new line down here and save my work. Now let's create a new executable. So in mypy package, let's go to new file. Let's create TF2 Turtle Broadcaster. We'll need our 3 very common packages that we use to create and run nodes. First, we need rclpy. Then from rclpy.executors, we'll import that shutdown exception. And then we will import node so that we can subclass it to create our own node. In geometry messages.message, we will import this transform stamped. That's what we're going to be broadcasting to because TF2 knows what to do with that. That's a message we need to construct. Turtlesim has its own interfaces. So in turtlesim.message, we will import the pose interface. We also need TF2 ROS. That allows us to work with the TF2 library. And then we're going to import that util file that we just created. Notice that we want to do it from the mypy package, as during runtime, ROS2 will know where to find that and then import that file for us, or that module for us. We will construct a class for our node. We're going to call it TurtleTF Broadcaster. This will continuously broadcast the transform from the world to the turtle frame. As we've done before in previous episodes, we will create our constructor. The first thing we do is call the parent class's constructor. giving it the name of our node, in this case, Turtle TF Broadcaster. Then we need to declare some parameters. This way we can change which turtle we are creating a broadcaster for, in case you, for example, have multiple turtles and you want to broadcast those transforms for all the turtles. We will declare the child of the transform, and it will default to turtle1, and then we will declare a parameter known as the parent. This is the transform from the parent to the child, so we will call the parameter parent and set it to default world. Next, we want to get those parameters and set them to our private member attributes, in this case, child and parent. Then we will create a subscription to the turtle's pose that's getting published all the time to the /pose topic. We will give it the interface, which is pose, that comes from the Turtlesim package. Then we need to give it the topic, which is / the namespace. In this case, the namespace should line up with the name of the turtle. So for example, turtle1, and then /pose. That's our full qualified topic name. And then we declare our callback, which is going to be self._broadcast, as that's going to be a private function we're going to make. And then the buffer size, which is just 10. The idea is that every time a new pose is published, which is happening a bunch of times per second, this broadcast function gets called, and we're going to use a TF2 ROS transform broadcaster to send out that transform broadcast. So we will store this in a private member variable, and that is a transform broadcaster object found in the TF2 ROS library. Then we will just log something to the screen showing that the broadcaster has started, and we will make sure to log which parent and which child. Now let's create our broadcast function, and in it we're just going to broadcast the turtle pose as a transform. And let me correct my spelling here. As we've done with topic messages, we're going to do something similar with our broadcast messages here. To do that, we will construct a transform stamped message by using this transform stamped object. Stamped means timestamp, so we have to provide a timestamp with this message. Scroll down so you can see what I'm doing. In order to provide this timestamp, we use the getClock method that's in the node superclass, and we will, from that object, call .now to get the current time, and then .toMessage, which makes the message format line up with this expected timestamp format. Then we need to provide the parent and child frame IDs, and those are just the names that we passed in as parameters. So to assign those to this message, we use the transform stamped object.header.frameID. That's the parent ID. And then we have the t.childFrameID that's set to the child. So for example, this will be world and this will be turtle1. As you can see where we've set those here as the defaults. Remember that a pose consists of a position in space as well as the orientation, or its rotation in space. We'll first fill out the position information, also known as translation. So we will set the transform stamped object.transform.translation. We will fill out x to be the message.x we get from that message. Remember, this is the pose information coming to us from Turtlesim about that particular turtle. This will be the x and y coordinates of the turtle in its parent frame, or in that world frame. Z is going to always be 0 since we don't have that third dimension. Then we need to fill out that rotational information, or its orientation in space. This is where we're going to use that Euler to quaternion function that we created. We're going to pass in 0 and 0 for the roll and pitch, and yaw is going to be the theta that we get from that pose information that's part of that message. Q is going to be our tuple that's returned from that function, and we can break that apart into the W, X, Y, and Z components of our quaternion. That transform stamped message format has transform.rotation, so we're just going to fill out X, Y, Z, W from those tuple components. So the first one is X, second one is Y, third one is Z, and the final one is W. Then we will use the send transform function in our broadcaster object to send out that message, this transform message we just constructed. Hopefully you are quite familiar with this boilerplate by now. We're just going to define a main entry point, and then we will initialize and run the node, Make sure you give the node the correct name. This is the name of our class, Turtle TF Broadcaster, so that calls the constructor. Creates our object. We say rclpi.spin. In order to just run that node, we will catch any keyboard interrupts so that we can gracefully shut down. And then regardless of how this program exits, hopefully it hits this finally block where we can gracefully shut down the node and shut down RCLPi. And once again, if the name of this executable is main, go ahead and call that so we can call that within the Python context if this is being run as an executable. Add a new line here, save with Control S. Because we've added some dependencies here on ROS nodes, especially around TF2, we need to go into package.xml. You can see RCLPi, example interfaces, my interfaces, geometry messages. We're using a couple of those. And we need to say depend Turtlesim as well as depend TF2 ROS. That should tell the ROS environment that we are depending on those ROS packages. So save that with Control S. Go to setup.py and we need to add our executable here. We'll just say TF2 Turtle Broadcaster is equal to mypy package.tf2 Turtle Broadcaster and give it the main entry point. Go ahead and save. Let's go to View, Terminal. Make sure you're in the workspace directory and say callcon build -- packages -- select and mypy package. With any luck, that should run and build successfully. Click that pop-up to get rid of it. And let's go back to our Turtlesim environment. So we still have Turtlesim running in our first terminal. In that second tab, we've got teleop still running. In fact, I can move the turtle around just to make sure. And then let's go down to our third terminal. We will go into config workspace. We will source install setup.bash as we've done so that ROS2 knows about this new executable we just added. And then we will say ROS2 run mypy package TF2 Turtle Broadcaster. That should start sending out the transforms from the world frame to Turtle1's frame. Now let's go to new tab and we will say ROS2 run TF2 ROS is this package, TF2 echo, which is a special echo command within the TF2 ROS package, and say from world to Turtle1. Oops, and it looks like I misspelled something here. Turtle1 exists, Turtle does not. So let's try that again. After a moment, it should start logging this transform information. You can see the translation. This is the location of the child frame in the world frame given in XYZ coordinates. This is in that parent frame, the world frame. So you can see the rotation in quaternion, radians, and degrees. Notice that this is about the z-axis, and it's given counterclockwise from the world's x-axis. Finally, you have this 4x4 transformation matrix. This is used in some matrix math. You can use these to chain together multiple transforms. This is what TF2 uses to translate from one frame to another. It constructs a chain of these matrices, does some matrix math to get you that full transform. So if I drive the turtle around, you can see the position changing, that translation, and you can see the rotation changing, especially as I rotate it around that z-axis here. Let's Control C to stop that. TF2 has this package called TF2 Tools that has some utilities in it. We're going to use this View Frames tool. So we're going to run this. It's going to listen to that transform data being broadcast for a few seconds. And then it's going to print out a graph for us. And it's going to store it in a PDF file. That's the easiest way to view this. So to look at that, you want to bring up a file explorer. I'm going to drop my mouse down here. You'll get the pop-up. You can view in folder, you can do the file manager, or you can go to applications file manager. If you go into the workspace where we've been working, and here is the frames PDF that we just generated. So if you double click that, there's no specific PDF viewer built into this container or this image, but the Firefox web browser will view PDFs. So let's open it in there. And here you can see this graph of how the broadcaster is working, how this transform is done from the world frame to the Turtle1 frame. It gives you the rate, the buffer length, and some information about that transform. As you can imagine, when you start having dozens of servos controlling a very complex robot, you can have multiple frames together, you can have frames chained together, and you can see how that whole graph looks here. Don't worry if TF2 is not quite clicking yet. It took me a while to wrap my head around what's going on. That's why we're going to revisit the concepts in the next episode and expand the simple example to include a listener. Hopefully, it will start making a little more sense. See you then.